Hi, this first video is going to be about one-sided limits, which comes from chapter 12, section 3 in our textbook. This has been introduced in class, and we've seen limits both approaching from the right hand side and from the left. So when we're talking about a limit approaching from the right versus the left, we see either a little positive symbol after our constant c, so the limit as x approaches c from the right for our function, or the limit as x approaches c from the left of our same function. Now we've already studied two-sided limits, which we spent a few classes on. When we talk about a left side limit, the left limit, we're saying that as x gets closer to c, but remains less, approaching from the left, but remains less than c. We talk about this corresponding output, the corresponding f of x, is going to get closer and closer to L, whatever that limit is. Likewise, with our right side limits, it's as x gets closer to c, but now remaining larger. So that's been our general discussion of what the one-sided limits look like as far as our definition. I'm going to put a specific example in here where we could look at something like the limit as x approaches 1 from the left, so we put that little minus sign, of our polynomial 2x cubed plus 5x. So to evaluate this limit approaching from that side, there are different methods we could use. We could look at a table, we could look at a graph, and as we build more known topics about continuity, we'll even be able to evaluate this limit faster. But without the assumption of continuity, we should look at either a table or a graph of this function. And so we can graph this function. I've pulled up the graph in Desmos here. So I have my function graphed. I've shown a window from like -2 to +2, and let's say -1 up to +10. And where x equals 1 is our point of interest. We're letting x approach 1 from the left. So approaching from the left, we see as we get closer to the whole number 1, the output, the y coordinate here, is getting larger, right? We're at 4.8, 4.9, 5.1, 5.2. And as we keep approaching and getting closer and closer and closer, that output is getting closer and closer to being actually 7. So the limit, based on our graph, or if we were to use a table as I've shown in class, would be 7. When we're dealing with the limit of a function, and the limit from the left and right hand sides are known. So let's suppose, this is like a little theorem or corollary here. Suppose that the limit as x approaches c from the left is equal to some number L, here it was 7, and the limit as x approaches c from the right is equal to r, some number that could be the same, could be different. Then the two-sided limit So let me get a little more space here. Then the limit as x approaches c for our function exists if and only if, which if with two f's is if and only if, the limit from either side is equal to each other. We can also say that we're able to say if the left and right hand limits are equal, then the two-sided limit, just the regular limit as x approaches c for our function, is equal to that number, either L or R, depending on which you prefer to use. So that gives us a little bit of information about how these one-sided limits play and how it's a little different sometimes than our two-sided limits. In class, I showed with a lot of different graphs how sometimes the limit from the left and the right will match and sometimes they won't. The other big topic that we have in this section is continuity. And we're specifically going to talk about having a function that is continuous at a particular point. And for something to be continuous, we sometimes say it just means you don't have to pick up your pencil to draw the graph. That is a very elementary way of looking at the idea of continuity. Our formal definition is that a function f is continuous at c if three things hold true. Number one, c is in the domain of f, or c is defined, or f is defined at c. So we've been talking about using the word domain a lot more. I'm going to phrase it this way. Likewise, there's two other conditions. One being that the limit as x approaches c from the left for our function must be equal to the output we get from just plugging c directly into the function. And the same must be true when we take the limit from the right. If all three of these things are true, then we can say f is continuous at c. A simpler way to write this is just to say that the limit, the two-sided limit, is equal to the output of plugging in c. So it can be written either way, and you will see that in our textbook and in our notes. So I want to wrap up this video with one final example where we're going to work with a piecewise function, and we are asked to determine where this function is continuous. So we're given a function, and it has different rules depending on where in our domain we are. So our first rule says x squared when or if x is less than or equal to 0. If x is between 0 and 2, exclusively, we use a different rule. We say x plus 1 if x is bigger than 0, but less than 2. And then our third rule, for when values are larger than 2, we use the function 5 minus x. If 2 is less than or equal to x, which is less than or equal to 5. So this is our piecewise function given, and we're wanting to know where is this function continuous. A great step is to observe what this function looks like by showing a complete graph. So if I'm looking at these if statements or when statements, the conditional parts that for our piecewise function, My domain here seems to be I'm allowed to plug in any number less than 0. I'm allowed to plug in 0. Between 0 and 2 is okay. The number 2 is okay. And anything between 2 and 5 up to and including 5. So values bigger than 5, I don't have a rule. So basically anything less than 5 is going to be part of my domain. So in drawing my graph, I want to be sure my x-axis also includes values up to and less than 5. So if that's -5, after 5, my function doesn't exist. There's no rule for plugging in the number 6 or 5.1 or anything like that. There's a few different rules here. So we may want to show on our y-axis some different values. Perhaps 1, 2, 3, 4. So I'm just going to go to 5 for now. It's a really good idea to always use pencil so you can always erase and redraw your graph. And then we begin to graph here. So the first rule is for when x is equal to 0 or smaller. So when x is 0, 0 squared is the rule I follow, which gives me a point at the origin. Numbers smaller, I get my parent parabola, but I'm only using the left side of it. So when I plug in 1, 1 squared is 1. When I plug in -2, -2 squared is +4. And I'll do my best here to kind of show this as accurately as possible. It's a little tough on the virtual whiteboard. But we get this parabolic shape. The line does continue to grow, so when I plug in -3, I get out -9 somewhere up here, right? So that takes care of every value for x below and equal to 0. Between 0 and +2 for x, we use a different rule, x plus 1. So when I plug in 0, I don't actually use this rule. So I'm going to put an open circle. And then this is an intercept at 1, a slope of +1. So we can just count it up 1 to the right 1 if we would like to use that method. And we show that up until x equals 2, not including x equals 2. So notice I have 2 open circles on that line segment. Then, after we get to the number 2 until the number 5, we use a different line, 5 minus x. So 5 minus 2 is 3. So 2, 3, which happens to line right up with my other line segment. 5 minus 5 is 0. And you'll see this is a slope of -1, which is exactly what we need. So this is a full graph of my function. So where is this function continuous? Are there any places where f is discontinuous? So looking at our function here, we see the pieces of f are each continuous for every number since they're polynomials. Right, the x squared, x plus 1, those individually are all continuous everywhere in their domain. Which means as we graph the different pieces, we're not lifting our pencil anywhere. When we graph this function, though, altogether, we have to be careful because the pieces change. We change what graph we're drawing at 2 particular values, right? I changed what graph I was drawing when x equals 0 and when x equals 2. That's when I swapped rules. I was graphing the parabola till I got to 0, then I had to change rules. Then I was graphing this increasing line segment until I got to +2, then I had to change rules and I get this decreasing one. So we can pay some special attention to when x is 0 and when x is 2. Those could be 2 places where our function may not be continuous. And I can tell if it's continuous first by asking myself, for instance, at 0, is 0 in the domain? The answer is yes, I am allowed to plug in 0. Is the limit as x approaches 0 from the left equal to the limit as x approaches 0 from the right, which is the same number as when I just plug in 0. So when I plug in 0, I use the top rule. 0 squared is 0, so that's 0. The limit from the left and the limit from the right should also both be 0. So from the left, we are approaching this point, 0, 0. From the right, however, I'm approaching the point 0, 1. So it is not continuous when x is 0. I can ask the same question of x equals 2, and I'm going to put that work over here. So is 2 in the domain? Yes, I am allowed to plug in 2. I get out a particular number. Is the limit from the left and the limit from the right equal? And is it the same thing as if I just plug in the number 2 to the function? So from the left side, I'm approaching this point, which is the point 2, 3. So I see an output of 3. From the right, I'm approaching that same point, so same output of 3. And when I actually plug in the number 2, I'll scroll back over to my function for a quick second. 5 minus 2 is the rule I use, so 5 minus 2 is 3. So our function is continuous for all of the numbers in its domain except when x equals 0. And that would be how we can describe our function's continuous areas and where it's discontinuous. The final piece I want to leave you with in this video for section 3 is just a quick summary of some continuity properties. So there are some common types of functions where we already have discussed what their domains look like, but now we can actually talk about a property having to do with its areas where it's continuous or not. So if we have, let's say, a polynomial, and that should be a term familiar to you from chapter 11, when we have a polynomial function, the domain is all the real numbers. And that's what this symbol means. You could use the words all real numbers as well. And it's continuous at every number in its domain, or on all the values in its domain. When we have something like a rational function, we see like r of x equal to p of x over q of x, where p and q are some polynomials. The domain is basically all real numbers except our denominator can't be 0. So accept the values of x such that q of x equals 0. And given that domain, our function will be continuous at every number in its domain. There's a couple other types that are talked about, exponential and logarithmic functions, but we're not discussing those for our course. So you may see those in the textbook or in some other online videos that you may watch that I did not make, but those are not things we're going to talk about. All right, I hope you enjoyed this video. I hope it was very informative.